Hi everyone, I'm Steve Brunton, and this is a video lecture series called Data-Driven Dynamical Systems. Okay, so we're going to be talking about dynamical systems and how you can characterize them using modern methods in data science and machine learning, data-driven dynamical systems. So this is a very exciting, new and emerging field of essentially discovering and characterizing, simulating dynamical systems purely from data, using techniques in machine learning, regression. And this is really, really exciting because we have this explosion of data. So more data than we could ever have dreamt of 10 years ago across nearly every field. So climate science, neuroscience, disease modeling, fluid dynamics, the amount of data that we're getting from experiments, from simulations, and from historical records is really growing at an incredible pace. And at the same time, the algorithms in machine learning, in data science, regression techniques, kind of these applied math and statistics optimization techniques are getting much, much better. And so we have this great confluence of big data and great new methods. And we're starting to get to the point where we can discover these dynamical systems and characterize them purely from data. Okay, so this is kind of with machine learning and regression. And a few points I want to make. So there's a few things I'm going to talk about. This is the overview lecture, so there's going to be a lot of specific lectures diving into, actual case studies of how to discover and characterize and control dynamical systems with machine learning and regression. But there's a few things I want to do today. So I want to talk about what are the current limitations in dynamical systems today. So what are the unsolved open problems? What are the goals of dynamical systems? So what do I actually want to use these for once I've characterized them? And what are some of the techniques that are emerging to start to characterize these systems? Okay, so I want to give you kind of this big picture, mile-high view of how we're going to use data science and machine learning to characterize dynamical systems, why we can, why we need to, and what we're going to use them for. Okay. In general, we're talking about a system x dot equals f of x. This system might depend on time. So if it depends on time, it's called non-autonomous. If there's no time dependence, it's autonomous. There might be some control input u, and there might be some parameters beta, so some vector of parameters. And these could all be, x could be a vector, u could be a vector, and beta could be a vector. So let's just actually write down x is the state of the system, t is time, u is some actuation or control input. Let's just put in parentheses control. Beta are my parameters. And in general, my system might have a lot of parameters. So for example, if this is a model of an aircraft flying, then beta might be a function of the wind speed, the humidity, the altitude, how heavy the plane is, all of these things where the dynamics would change as beta changes. And u would be all of my control variables, like how far my flaps are extended or how high my elevators are and things like that. Okay? And then this f is essentially what we call the dynamics. So this is a differential equation. F is the dynamics. And also sometimes I'm going to call this a vector field, because essentially this f of x gives me a vector at every point x, and it tells me how fast x is changing and in what direction. Okay? So this is kind of the anatomy of a dynamical system. So this is called a dynamical system. A dynamical system, and this is the anatomy. Okay? So that's what we're going to be talking about. We're going to be taking data, measurements of x and t and u, and maybe beta, and we're going to be trying to characterize and build these dynamical systems models purely from data. So what did people do in the past? Okay, it's not like dynamical systems is new. People have been doing dynamical systems for hundreds of years. In fact, you might even say that Newton's second law force equals mass times acceleration is a dynamical system. It can give you the trajectories of ballistics. You can use it to simulate things like the pendulum dynamics or the planetary motion, which are examples of dynamical systems. In the past, traditionally, what you would do is you would take essentially a physics-based approach where you would write down Newton's law or the Lagrangian or the Hamiltonian for a system, and you would derive the equations of motion, this dynamical system, from first principles using physics. Okay? That's what we've done for hundreds of years since the time of Newton, is basically derive the equations of motion, these dynamical systems, from first principles, starting with something like F equals ma or the Lagrangian or the Hamiltonian. But increasingly today, the systems that we actually want to understand, like the brain or the climate or the financial market, there are no first principles physics that we can write down in an easy to understand, simulate, and control framework. So writing these things down from first principles is a non-starter in a lot of fields. There's no master equation for your brain. But we are increasingly getting more and more data. So there are recordings now that you can take of brains, and these recordings are giving us more and more larger and larger volumes of data that we can use to build models. So I want to point out also, this is very important, even F equals ma is not the kind of final word truth. The Navier-Stokes equations for fluids, these are all just models. Okay, so this is a model of reality. Very, very important that this is all just a model of reality. In the past, we used to use physics, F equals ma, Navier-Stokes equations, Schrodinger's equation. These are models of reality, and they're very, very good models of reality. You can build satellites and go to the moon with these models from first principles. But the next generation of problems for this next 100 years, like controlling turbulence or understanding the brain, we're not going to be able to use first principles physics models all the time. So we're going to have to derive these from data. Okay, so that's a huge transition as we're going from data, sorry, we're going not in the wrong direction. We're going from first principles. And this basically, first principles, I hope I'm spelling that right, first principles, and we're going to data-driven techniques. Okay, so in the past we would use F equals ma. Now we're going to try to derive this from data. And this is still in its infancy. There's much more you can do if you actually know the physics than what you can do with data now, but we're trying to build these data-driven techniques, we as a community, to be more and more powerful for these emerging class of problems. Okay, so there's two things I want to talk about. One is what are the challenges of these data-driven dynamical systems today, and then what would we use them for? Okay, so let's start with challenges. One key challenge, one of the biggest challenges, is that these are nonlinear dynamical systems. So I'm going to write that down, nonlinear. Nonlinear F, okay? So if this was a linear differential equation, if this was linear, something like x dot equals a matrix A times x, we would know everything about this system based on the eigenvalues and eigenvectors of A. So linear systems are completely characterized. This is linear. And I'm going to put a check next to it because we completely understand linear systems. But even a small amount of nonlinearity, an x squared or a x cubed or a cosine x in this right-hand side, makes it very, very hard to understand, predict, estimate, and control what will happen in the future. Okay? So nonlinearity is a huge problem in dynamical systems, and we're starting to get some techniques that might help with this. Maybe an even more fundamental issue is that these dynamics are unknown. So in a lot of cases, we have unknown dynamics, an unknown F. Right? So we don't even have a textbook equation for the brain. We don't know what the right-hand side equation is. We need to discover F from data. Okay, these are probably the two biggest open challenges, the two biggest problems, let's call these challenges, in modern dynamical systems that data can actually help with. is nonlinearity of the dynamics and the fact that we don't even have governing physics or equations of motion for a lot of systems. Okay, other issues that we have, I'm going to write these down. These are also very important, but they're not as primary. Oftentimes our dynamics are high dimensional. That's an I, high dimensional. Meaning the state vector x has a lot of components. It might have millions or billions of degrees of freedom needed to describe the system as a differential equation. So if you want to simulate the Earth's climate, then you need to take the Earth and chop it up into a bunch of grid cells, maybe a million or a billion grid cells, with 1 kilometer or smaller resolution across the globe to even get close to kind of simulating some of the features of interest. So it's a very high dimensional state vector x. You also have chaos, transients, and things like that. So chaotic dynamics and transients are quite challenging. Noise and stochasticity. So my measurements might be noisy and they might be stochastically forced. So in your brain, if you measure recordings of the brain, you're getting very noisy measurements of the system usually. And also there's a lot of underlying noise and forcing going on. The stochasticity, financial markets, this is a big issue. In lots of systems, if you're actually measuring data, it's going to have noise and stochasticity. So you have to take that into account. You also have multi-scale dynamics. So you get these kind of structures and coherence across multiple scales of space and time. So turbulent fluids are a great example of this. They're very multi-scale. You can zoom in and zoom in and zoom in, and there's still structure. Okay, that's very hard for modern dynamical systems. And then maybe a last one is uncertainty. So oftentimes I have uncertainty in my initial conditions, my parameters, the dynamics, and we have to understand how to handle and propagate that uncertainty. So this is, the two primary challenges, but there's a lot of other, okay? And this is really just my perspective. I'm sure if you talk to another dynamical systems person, they'll give you a different list of what they think are the biggest challenges in dynamical systems. This is kind of my to-do list, right? We're focusing our energy with my collaborators on essentially using data to solve some of these challenges in modern dynamical systems. Okay, so think of neuroscience, turbulence, financial markets, disease modeling, anything like that that's high-dimensional, multi-scale, nonlinear, and where you don't have known dynamics F. Those are the systems we're interested in using data for, okay? Good. So now the other side of this is what do we actually want to use these for? Okay, so these were the challenges. What are some of the uses? Okay, so uses of models. And again, this is not the definitive list by any means. This is just what I think of on a day-to-day basis. So kind of the most obvious thing that we would want to do if we had this dynamical system is we might want to try to predict the future. Okay, so we call this future state prediction. Okay, that's very important. And future state prediction might not just mean of one trajectory or one initial condition, but I might want to run an ensemble of initial conditions. I might want to get a probability density of how the future state evolves. So in the climate, we're not really interested in how one trajectory evolves. We're interested in the probability of the state evolving in one direction, maybe higher temperature, or another direction, lower temperature. So this might be an ensemble or a statistical description of the future state. Okay? Another thing we might want to do is use it for design and optimization. Okay, design and optimization. So one really big application of data-driven modeling and first principles modeling today is in Formula One race cars and also yachts. Okay, so the kind of World Cup design. So in both of these applications, you have very complex systems governed by fluid dynamics, turbulence, this kind of complex multi-physics system. And depending on if it's raining or not, or if it's a humid day, or if you have, a certain type of airfoil scoop on the back of your race car, these parameters, the dynamics might change quite dramatically, and you might have higher drag or lower drag. And so a lot of effort is going into using reduced order models of this very complex system to then optimize rapidly and develop better and better race cars and better yachts. Okay. Another goal I think is very important is control. So I might want to actually, it's slightly different than design optimization. So in control, I can actually measure my system, and with a model of the system, I can design an actuation signal to modify its behavior actively using sensor-based feedback. So this is a major goal in lots of systems. So let's say suppressing seizures in a brain, or suppressing disease as it spreads through a continent, increasing the power output of a turbine that's interacting with a fluid flow. So control is really important. And one that doesn't always make the list, but I think is maybe as important or more important than all of these, is this idea of interpretability and physical intuition. So interpretability, and physical intuition. I think this one is extremely important because what we're talking about is we're going to be using these machine learning methods to characterize dynamical systems. A lot of machine learning methods are fundamentally hard to interpret and don't give you intuition. So I am a very strong advocate of tailoring the machine learning methods so that when we get dynamical systems out, they're interpretable and they give us more intuition about the physics of the system than we had before. We actually want to understand the system, okay? So we have challenges, we have what we actually want to use these models for, and then maybe one of the last things I'm going to mention are just some of the techniques that I think are really powerful. So techniques. And this is, again, very incomplete list, but some of the techniques, I think regression is probably the foremost one. So regression, linear regression, I think is a big one. Sparse regression. These are techniques that we're using a lot to get dynamical systems models from data, is just regression models, linear and sparse. Neural networks, so neural networks and deep learning are becoming extremely powerful techniques to learn these dynamics from data. These often suffer from interpretability issues, and so I'll talk about that, how we can build these networks and constrain them so that they are interpretable by construction. And then there's a lot of other methods, so I think genetic algorithms and genetic programming have been used very effectively for discovering dynamical systems from data. Okay, so that's really kind of the high-level overview. We want to discover these dynamical systems from data. We want to be able to cope with nonlinearity, high dimensionality, chaos for these goals, and there's a lot of emerging techniques that we're going to talk about. So we're going to dive into all of this. We're going to go super deep into some areas and more topical on others. For example, nonlinearity. There's a new field called Koopman analysis, where essentially you're trying to find a coordinate transformation. Let's say for this nonlinearity, we're trying to find some new coordinate system, phi of x, so that ddt of phi of x is linear in those new coordinates. So we want to find these coordinate transformations that make my nonlinear dynamics look linear. Okay, that's a long held goal of the physics community. In fact, a lot of physics is trying to find coordinate transformations that make your system simpler. But now people are using deep learning or sparse regression to find these coordinate transformations from data. So that's one concrete application of how we're coping with nonlinearity using these methods. We'll also talk about how we can discover F using these regression techniques and what we can do. So one last parting thought. So this is going to be a full lecture series with lots of methods. We're going to talk about emerging methods like the dynamic mode decomposition, Koopman analysis, delay coordinates, neural networks for learning these dynamical systems. One thing I really want us to everyone to take away from this is that most of machine learning was developed for static tasks like image classification or scene labeling, things like that. But we know that our dynamical systems do in fact have physics. There's constraints, there's conservation of energy, there's F equals ma, there's all of this stuff. Even if I don't know the exact equations for a turbulent fluid or a reduced order model for it, I still know some basic physics. I know that energy is conserved and mass is conserved. Even in systems where I don't have dynamics, like the brain and epidemiology, there are surely constraints and symmetries and invariants, kind of the physics of those situations. And so one of the really important things in combining machine learning with dynamical systems is extracting the physics of the system. That goes to this interpretability and intuition. But also, if you know something about the system, if you know that energy is conserved or mass is conserved, you can dramatically improve the learning of these systems by enforcing those constraints, enforcing those symmetries and those conservation laws directly in the learning procedure. So we'll show that you get more interpretable models. You can learn with less data if you bake in what you know about the physics into this dynamical system learning procedure. Okay, so I'm excited to take you through this. This is an emerging field. It's really, there's a tremendous amount of potential. Already people have made incredibly impressive and powerful demonstrations of how to discover dynamical systems from data. People are making progress on these high-level goals, but this is a rapidly emerging field. And so, if you get interested in this, you can directly help move this field forward. Okay, more to come. Thank you.